Hi and welcome back to the fourth outcome in our 239152 little series here. We're going to discuss outcome 4 of the 239152 course, looking at the required outcomes that you have to have prepared for your assessment. So we're going to discuss what you'll be assessed on for this outcome. And this outcome is a big one. This one covers the understanding of the requirements for testing. Okay, so we've done inspection in outcome 3. We're not going to go on to testing. It's all going to be theoretical. There will be outcome 5 where we'll actually look at doing some performance there. But as you can see, outcome 5 isn't assessed on a theory assessment. Outcome 5 is a practical assessment. The theory assessment is greatly consisting of outcome 4, over half of it. So we're going to go through this at a pace, hopefully, that you can follow. And remember, we're just going to talk about what the outcome is, how to achieve it, and your training, your 239152 training, or your 2391 whatever training, should make sure that you have all of the training required to achieve this outcome, because this is what you'll be assessed on. So, you have to understand the requirements for testing electrical installations. 4.1. The learner can state the reasons for the instruments to be maintained and comply with standards such as BS7671 and GS38. Okay, so you don't say they must be to GS38 or they must be to BS7671. We have to actually explain why and what those methods are that require compliance. So we have to make sure that we regularly check them, that they're not damaged, they're not corroded. We have to make sure that any tips are still on. So if you look at GS38, the criteria there, the tips to be no bigger than 4 mil, preferably 2, to have finger guards, to have obviously high current resistors in there now. They've retracted diffusers to make sure that they're distinguishable from each other, to make sure that they are rigid and long enough. Okay. Got to make sure that you have all that understanding, but mainly that you check them and you maintain their quality and you store them properly. We'll also talk about calibration or self-checking, which one is best or which ones we should be doing. The importance of checking before use. We'll check the leads before use, we'll check the batteries before use. There's no point using an insulation resistance setting on your test instrument which heavily relies upon the battery power of your machine. If your batteries are insufficient, you're not going to actually be able to apply the actual required voltage and current to do the test. So there are some key initial checks to make. There are requirements in BS7671 for the values of the test instruments, the voltages that are applied, 4 volts to 24 volts for continuity, for example. We'll look at those later on. Okay, but it's not that you have to say they must be compliant to GS38. You have to actually explain what the requirements of GS38 are. You have to be able to actually blow that up a little bit. Describe the characteristics of instruments and the leads used for each test. Okay, so to start off with, make sure that you understand what to call the tester. So we would call them the low resistance ohm meter, the insulation resistance tester, the earth fault loop impedance tester. We wouldn't call them your MFT or your mega or your fluke. We have to make sure we have the right terminology for the instrument. We also need to make sure that we understand the characteristics of these instruments and their limitations. So the low resistance ohm meter, which we use for continuity, there's the voltage there, 4 to 24, etc. It only measures in the ohm and the kilo ohm range. It doesn't measure in the mega ohm range. If we're measuring continuity in the mega ohm, we clearly have it set on the wrong thing. So the low resistance ohm meter is commonly used for continuity of protective conductors and continuity of ring final circuits. The clue is they are used for continuity measurements, which, you know, it's an essential fault finding test that we use. We have the insulation resistance tester. So this again, you can see here, this is the continuity setting on an instrument, and here's the insulation resistance testing on an instrument. It's the same one instrument. It's what we would call an ohm meter, but you have the low resistance ohm meter, and then you have the insulation resistance section. The difference here is the applied voltage. The continuity had 4 to 24 volt short circuit test current of 200 milliamp. The installation resistance tester will be anywhere between 100 to 1000 volts. That's DC. So, I mean, we typically would use 500 volts. We may go down to 250 on your typical low voltage system. But the value that we will collect will be in the mega ohm, and so you need to understand how to actually read the scales on your instruments. And the mega ohm is the million ohm. So a 3.44 ohm, 3.44 kilo ohm, and a 3.44 mega ohm are completely different scales and completely different areas. So do make sure you have it on the right setting and you understand how to read your scale. The earth fault loop impedance test, though, in this case it's another instrument. If you have a multifunction tester like my 1720 mega, then it's just another setting on the instrument. But if you have a dedicated dead test, live test instrument, then you may have a separate earth fault loop impedance tester. The earth fault impedance tester will be used for measuring the external earth fault loop impedance, ZE, your earth fault loop impedance at subsequent distribution positions and at the end of every final circuit, your ZS's. It must have the ability, well, should have the ability to go to a no-trip facility. The no-trip facility being a little selector there. Now, some testers will go default no-trip. The QTech KT65 I think does, where you turn it to loop and it's on by default. It's got ATT on it, and the anti-trip technology goes to no trip as a default, and then you have to come from low current to high current. I understand that as a safety measure, so you don't trip RCDs unnecessarily, but I mean, that's a bit of a pain in the ass for people like me who actually kind of like to be in control. But if your tester doesn't have a dial for each, it might be that it has a button, like a function button, where you turn off the anti-trip on it. But fundamentally, understand what the instrument is there to do. So the earth fault loop impedance tester is there to test earth fault loop impedance. That's fairly plain and simple. They can also be used, though, to obtain values of prospective fault current. This is done by pressing a button after you've done a measurement. So here you can see a loop test. If you were then to press the PFC, it will just use Ohm's law, and it'll turn that 1.4 into a currently reading by looking at the voltage that was on the circuit that gave us that reading and dividing that voltage by that reading to give us the equivalent current value. This is how we obtain a value of prospective fault current by measurement. We calculate it from a measured earth fault loop impedance. What you will need to bear in mind, though, is if you are measuring an earth fault loop impedance such as ZE, where you have removed your parallel by removing the main earthing conductor that what you have to test on, you can't then just press the button and obtain a prospective fault current at the origin, because you have to have all of the potential parallels of the bonding and the metal framework and everything as well in circuit. So you need to measure ZE on the ohm setting, reconnect the earthing conductor to introduce all of the parallels, and then do the measurement again, but set onto PFC. Sometimes these instruments that have the ability to calculate from one to the other don't really help you, because they try to speed you up when really you're kind of working competently if you're not aware of these problems. Similarly, you may need to measure the prospective short circuit current, because the prospective fault current is the value of the prospective earth fault current and prospective short circuit current, and we record the highest as the prospective fault current. With 3 phases, it'll be a PSCC between 2 phases. We need to be able to test those as well. So again, you may notice your loop tester doesn't actually say earth fault loop, it'll just call it loop. Or maybe your dials are between live to earth but also live to live or live to neutral. That's the idea, where we can have a loop test carried out between 2 lives or between line and neutral. If you're thinking, why would I need to do that? It's mainly because of the ability to obtain a prospective short circuit current reading or a prospective fault current reading. I also would use a value in my area where I do work as well with arc flash. So I would do a value of live to neutral loop, so I can actually get an understanding of the impedance of that path as well for arc flash calculations. But yeah, do be aware of what the testers can do. Earth electrode resistance tester uses a dedicated earth electrode tester, which is essential for generators Or if we have a TT system and there is an RCD on the supply and the supply is energized, then we can use the earth full loop impedance setting to do a ZE test on the origin side. But if there is no supply, or you're on a generator out in the middle of the sticks, you'll need to have a dedicated earth electrode tester where you'll then be planting a potential electrode and a current electrode in the ground and measuring in between the points. If you read through guidance notes 3, that's all in there. But there is questions on the types of electrode resistance tester. We have the earth full loop impedance tester, we have the dedicated earth electrode resistance tester, we also have the stakeless type. So that's a very common question, is, which type of earth loop electrode resistance tester would we use if we were doing a generator? That's a dedicated one. If it was a TT system, we could use earth full loop impedance tester. Okay, so be familiar with the 3 different types of electrode instrument now. The RCD tester needs 3 scales. These are the times half, times 1 and times 5. We need the times 5 for when we're verifying the additional protection requirement for ADS. Times 1, times half for all other types of RCDs as well. There may be a ramp test facility. These aren't needed, but they're very useful. They're very good at assessing nuisance tripping or sensitive RCDs. In each test, the required RCD, the voltage must not rise above 50 volts AC RMS, because when we obtain a voltage over 50 volts AC RMS potential on the Earth, we are then reaching a potential Earth that is now becoming live. It's now, the environment is going from ELV to LV. We must make sure that we don't do that, and there are 2 ways that we do that. The first way we do that is we always do an earth full loop impedance test first. We'll always do an earth full loop impedance test to make sure that the local area has effective earthing, so that there is an unlikely event where the voltages may rise to this high potential. The second way is the manufacturer. The manufacturer will have an inbuilt limit of 2 seconds. So you may notice that your times half doesn't actually come up as no trip on the instrument. It might just say greater than 1999 milliseconds, which is 2 seconds. Okay, so the manufacturing standard implements a limit of test of 2 seconds, just in case we have these increased potentials of voltage in the local earth arrangement. Checking of instruments. Instruments require regular testing and calibration. It should have a current test certificate, and the normal time span between these should not be more than 1 year. Now, this is a common trend that we have in the industry, where we would send our instrument to a calibration house and we would have a calibration certificate, something similar to this one that I've got from my Mega instrument here. But it's it's a once a year thing. What is also expected from a competent person would be a way to maintain the accuracy or monitor the accuracy of your instrument between these checks. I, for example, see if I can find it, I would use a simple spreadsheet just to record my data. Here we go. Let's slide this over here. So this is a Mega 1720 that I've got. So I monitor the continuity. I have basically some resistors that I got from Maplins, but you can get little checkboxes and things. And I just take a measurement and compare it to the actual value of the resistor. I do it monthly. I also verify the installation resistances, and I have a benchmark point in my house where it's a socket no one uses, and so I regularly use that as a reference point for verifying the earth full loop impedance as well. You can see in this month here, the readings were a little bit high, so I pulled that aside, looked at the leads, and it turned out that my line conductor had a bit of corrosion. The spring contact was a bit rough, so I bought a new lead and it was fine. But this is an example of just showing a little extra diligence and taking extra precautions there and controlling your work better. Relying on an annual calibration, it's risky. I would rather use that kind of system more heavily than an annual calibration myself. You must make sure that the equipment, as far as electricity work is concerned, regulations are concerned, are fit for use, and they're used properly and they're appropriate for the task. So to be fit for use, they need to be free from damage. They need to be free from. They need to be they need to be suitable. An example being a voltage indicating device needs to be with the tips on. It needs to be free from cracks, free from damage to the cables. It must be used properly, so the person using the equipment must be trained or competent or both on how to use the equipment. Competence is overall where we want to be. They can maybe be instructed, but again, how accurate is the instruction? You don't want to give a guy a tester and say, here, just use that button, then leave them on site with other risks that could crop from that. Appropriate for the task, yeah. When we go to prove isolation, for example, we use a GS38 voltage indicator. We would not use a neon screwdriver type instrument. We also wouldn't use a multimeter when we should be using a multifunction tester for testing electrical installations. So make sure it's suitable for the job that you're asking of your instrument. The accuracy of the instruments can be judged in two ways, as we've just mentioned: the regular checks or the annual calibration. Okay. The learner can explain why there is a recommended test sequence for initial verification, but not really a recommended test sequence for periodic inspection and test. So this is where we have to understand the way that we approach the work in the two different areas. Remember, the initial verification is the testing of a new system, so there is an essential criteria we must follow, and there is an essential sequence. These are two common examples. So example 1, we may have a short circuit between earth and line that occurs on a circuit after a break in the protective conductor. So if I have a cable and the protective conductor is broken, let's say that I've got a light circuit and the protective conductor going to the second light has been disconnected at the ceiling rows, and then beyond that there's a short circuit between earth and line in a luminaire. Now if I was to do an insulation resistance test between line and earth on that circuit, I wouldn't detect that short because the protective conductor is broken, so the test isn't going to find that in the circuit. If I was to then, after the installation, do the protective conductor continuity test, I'll find the broken protective conductor, fine. I'll remedy the broken protective conductor, but what the idea of the sequence is, I wouldn't go back to the beginning and redo all of the tests. I would repeat the protective conductor test, and I'd then move forward. Potentially then I'd be energizing a circuit with a line to earth short. So if I do the protective conductor test first, continuity test, I would then find that, fix that, and then the next test, subsequently the installation, I would find the line to earth short as well. Another example, as we mentioned just a minute ago with the earth for loop impedance testing and the RCD testing. The RCD test requires an effective earth for loop impedance in order to maintain a safe voltage under the test. If we haven't verified that the earth for loop impedance in the area of the test is sufficient, then the potential voltages during the test can rise to unsafe levels. So there is a need to have a sequence for testing for initial verifications. With regards to periodic inspection, the whole idea of testing is supplementary to inspection, which is it's how it's supposed to happen, but it's not how it happens. What happens is electricians go to places and there'll be software, Amtech or Trimble, whoever they are now, you've got NIC, you've got all these softwares, and the whole idea is, here's a load of certificates, go get numbers to fit in the certificates. At no point is really there any time for a sufficient inspection. I even know companies that pay per circuit. You know, if you pay an electrician £5, £4 a circuit through an agency or something, the last thing they're going to do when they arrive on site is do suitable, effective inspections. They're going to look to collecting all of the data, which is what they get paid for. So there's a big problem. But what you need to remember is the whole idea of periodic inspection and testing is to use your inspection skills, your ability to see an existing system, to assess it against the current environment, to assess it to be used for the future in that way that you're seeing it. So a change of use, a change of ownership, a change of demand, is it still suitable? Is there age? Is there wear and tear? Has there been a flood? Is it still suitable to carry on being used? All this will be done really with suitable inspection, and this could be visual inspection, it could be talking to people, asking questions. What's the demand? What's the use? Who uses that? When does this go on? All of these are questions and answers and inspections. If we want to test something, we may then test just to support our inspection. Testing is supplementary to inspection. Inspection is the key. I just wish it actually worked that way. The assessment criteria. Okay, no, 4.4. The learner can explain why certain tests may not be necessary at periodic inspection and tests. We actually briefly covered this on the Outcome 3 video. Installations that have been previously tested with comprehensive records of tests, they may not need the same degree of testing as installations which have no records. Yeah, if we have no records, we should start creating records so that there's proof of maintenance and proof of traceability. If there are records, we can then just update, supplement, or just take them on board. Okay, the tests considered appropriate by the person carrying the inspection should be carried out. Okay, this has got a bit small just to fit it all in, but the learner can, and we're going to do two at once here, 4.5 and 4.6, explain the purpose for each test and describe how the test is carried out and how it may be adapted for periodic conditions. So that's two tests. We first of all will describe it for initial verification, and then we'll say how it may differ in the periodic inspection condition. So the first one is the continuity of protective conductors, including main earthing and supplementary bonding. What's the purpose of that test? Well, the need for a protective conductor, especially if our protective measure is automatic disconnection of supply, is to verify that it's at every point where that protective measure is needed. If I have a class 1 luminaire, a class 1 oven, a class 1 item or a socket outlet, and I plug in class 1 items of equipment, they rely heavily on the presence of the protective conductor or the earthing to take away the current and earth fault condition, and we must verify that that conductor is there. So the continuity of the protective conductor is to verify that the protective measure of ADS is achieved. Similarly with supplementary bonding conductors, the whole idea of the touch voltages, we need to verify the continuity of the main protective bonding and the continuity of the supplementary protective bonding, all to verify that the touch voltages do not exceed 50 volts. How the test is this differing to periodic? Well, on the initial, you'll probably do it as you install, or maybe towards the end, but you'll have an understanding on the layout of the circuit, so you would have a good understanding of where the final point of the circuit is. You may do an R1 plus R2 test, the method 1, or you may do the R2 test, method 2. On initial verification, you most often will do the method 1, because the R1 plus R2 test will also give you polarity and functionality. And you'll have to do it on every single light point to verify polarity and functionality with the local light switch as well. But you'll find that method 1 will most often be adopted. Now, from a periodic perspective though, it may be that you choose to go with method 2 because of the fact that you don't want to dismantle too much, or you may have a limitation. I see some electricians that will say, oh, there's a limitation, we can't turn off the lights, so they'll put a limb, and then that circuit's not been tested, but they'll still charge for it. You can still do a continuity protective conductor test with the method 2 test, the R2 test. It's only 24 volts. It's absolutely fine. So you can go doing that. The only issue there is the wander lead method, the R2 method, may introduce the trip hazard. So there is that concern, but you don't just say, oh, I can't do it because we can't turn the circuit off. So in the periodic, it may be converted to doing the R2 most often. Continuity of ring final circuit conductors, how is it carried out? Well, again, I mean, I'll be honest, it's best to probably go forward to a dedicated video on it instead of covering it all verbally, because it's a lot of waffle. It's best to watch a dedicated video on an individual test to actually kind of understand that. But we understand with the ring final circuit, we have the 3 steps, step 1, step 2, step 3. The first step will be the end-to-end, little r1, little rn, little r2. The other 2 steps will be the r1 plus rn and r1 plus r2 test. The whole point of that being verifying that your ring final is a ring final and that there are no internal loops. What you need to do is understand or be able to explain why there's a potential there. What the problem would happen if we have an open circuit. So we may have obviously a 2.5mm cable on a 32 amp MCB, overcurrent protection being an issue there. So explain why those tests are done. For the periodic condition, as we saw on the prior video, you may not need to do ring final circuit testing. It's considered that if you have existing maintenance and there's no changing or alterations, then you may not need to do it. If you do choose to do it, then you may find that you'll have to obviously de-energize the circuit, but you may find it that you do it at one point and then just sample the other points to do it at. I think the common attitude with the continuity of ring final really is to verify internal rings and broken circuits. My personal perspective would be, if I had no evidence of alterations, new circuits where additional rings within the ring could have been installed, I'd probably waive that test. But I would never waive the end-to-end, because anyone could have changed the socket and put it back and left a conductor off. So I'd always still do step 1 of the 3 steps, that's for sure. Insulation resistance. Explain the purpose of that. Oh, make sure that there's no degradation to the insulation within a system. That's fairly obvious. When you install cables on initial verification, running them through joists, you have one conductor sitting still, you have the other conductors rubbing past as you pull them through. That one that's sitting still with all that friction, the insulation could be worn away. You may have, when you put the floorboards down, you may have nailed through a cable. You may have someone put a screw or kitchen cupboard through a cable. You don't know what happens during an initial verification. So we must always do our installation tests for every single cable and circuit we've installed. For an existing system, though, for a periodic, we're more thinking mainly about maybe some mechanical damage, but it's most likely going to be things like moisture ingress or heat damage. So we will still test it as much as we can. There will be a big excuse in the periodic world that we have to limit this test because we can't take stuff out of line and from between line and neutral. That's fine. You can always do those two in parallel to earth. You'll still get life to earth that way. So life to earth should be achievable. Down a more detailed route, you may need to consider things like protective conductor currents and stuff, and filtering if you go between live and earth. You may get some feedback. But again, it all depends on your knowledge of the equipment that is in the circuit, really. But yeah, insulation resistance on a new install must be done. On a periodic, I'd like it to be done, but I often would see that it's just limited. What I'm also seeing is it being limited or being ignored, but contractors will still put greater than 200 or greater than 999 because that's what they've always seen, which is a bit of a concern. Self, PELV or electrical separation. You may not come across this one. This is where we've installed the protective measure of self and PELV or electrical separation instead of or as well as ADS. The main concerns here is we have extra low voltage for the self and PELV, so we have to have them of a separate band voltage, band 1 from band 2. They must be segregated from LV unless they're wired to the same voltage. And with regards to self from PELV and self from LV, self is earth free, so we would not install a self system within an earthed containment because we need to keep it separated from earth. So you separate self from PELV, self from LV, and self from earth. With regards to electrical separation, like a shaver point or anything like that, again, if it's only one item, that's fine. But if it's more than one item, if we have electrical separation feeding 2 items, we have to segregate them from everywhere else. FELV, functional extra low voltage. This is more of a, you may see this in control panels and in some factories and things, but again, it's more a case of segregation, but for the purpose of function. It's not for the purpose of protection. Barriers or enclosures provided during erection. And this would be an initial verification. I don't see how during erection would be considered on a periodic. It just wouldn't. But when you're doing your initial verification, you're doing your install, you may have applied insulation due to high access area, high working area, or you may have cables that haven't been properly covered up yet. So you may have some supplementary barriers or some supplementary insulation in the way for a temporary period of time. Insulation resistance of non-conducting floors and walls. These are mainly in manufacturing or in medical areas, really, from my experience, but it's where we've got an earth-free location. And if you look in the wiring regulations, there's a whole appendix on this. I'll be honest, in the 2391 you're not going to really have any kind of questions on it because it is quite a niche area. It's one of those areas where if you work in that environment, you will have to probably read some textbook just to make sure you're following the additional rules. There are additional measurements and additional values that you will need with regards to the probe electrode and things like that. Polarity, there are two types of polarity. There's obviously the dead polarity and the energized polarity. The dead polarity mostly will be confirmed on the initial verification with the continuity of protective conductor test, the R1 plus R2, but you'll need to verify that polarity is there for 3-phase, for triple pole switches as well. If you're doing just the R2 test, or you're working on a periodic and you're just doing the R2 around, then you need to say, how are you verifying polarity? Will you consider your ZS test as a verification of polarity? So, you need to make sure you verify polarity one way or the other. And if you think of the regulations, do remember those 3 things that you must verify with polarity there. So the wiring regulations will tell us that we need to have the center contact of the ES lamp holder must be line, the outer thread must be neutral. We must make sure that single pole switches are switching in the line conductor only, and correct connection and accessories and stuff. And I'm going to do another video soon or later, but there is a big problem with the R2 adapters creating a bit of a polarity problem when testing, which I'm going to cover in another video at a later date. Earth electrode resistance, if applicable. Is it for a generator, or is it for a TT system, or is it for an EV charging point, or is it for a TNC system, as we're going to be seeing forward with the 18th edition next year? Yeah. If it's a dedicated electrode, not on an energized system, it must be an earth electrode resistance tester. If you have a source of supply and you have a suitable RCD in place, you can use an earth electrode resistance tester to verify it. Sorry, an earth fault loop impedance tester to verify it. The earth fault loop impedance, explain the purpose of this test. The earth fault loop impedance test is to verify that the earth fault loop resistance, or the earth fault loop impedance path, is of sufficiently low resistance that when you calculate the equivalent current that would flow, the resistance is low enough so that the equivalent current is high enough. And we need the equivalent current to be high enough so that we can achieve disconnection of the device in a time that is quick enough. So it's kind of like, okay, we need this low resistance to achieve this high current to achieve this quick time. That's how we actually chase that. So when you look in the wiring regulations and you have your maximum values of measured earth fault loop impedance calculated, or you refer to the tables, they are using Ohm's law from the time current characteristics within Appendix 3. So that is the purpose of the earth fault loop impedance test. It's one of the most important tests, because again, the whole principle of an inspector is to verify that the wiring regulations protection for safety, the Chapter 41, has been complied with, and we do that with earth fault loop impedance tests fundamentally. Additional protection, the testing of disconnection times for RCDs. Yeah. When additional protection is needed, and the method to achieve additional protection is via the use of an RCD of 30 milliamp, we've got to verify that when we test it at times 5i delta n, or we put 150 milliamps through that 30 milliamp RCD, that disconnects within 40 milliseconds. We only do the 5i delta n tests to RCDs up to 30 milliamp, and we only do it if additional protection is the reason that we have that RCD. Prospective short circuit current. It's worded like that, but it's really prospective fault current. I think the short circuit current is commonly put ahead of that, because with regards to 3-phase systems, we have the short circuit between 2 phases. If we have a TNCS system, though, we do need to remember that whilst the TNCS system uses the neutral as a return path, and so saying it's a prospective short circuit current will give us the equivalent, if we have parallels, water systems, gas systems, structural framework, then potentially the prospective earth fault current may be higher than the prospective short circuit current on a single phase system, because you'll have the parallels supporting the lowered resistance of the earth fault, whilst with the short circuit you won't. So it might be worth just considering those, but fundamentally the idea is to make sure that the value of fault current, be it short circuit or earth fault, has been measured or calculated or inquired, and we then look at the current and we make sure the protected devices that we select and that we introduce at the point, either at the origin or subsequent distribution points, is going to tolerate that energy level. We have terms like breaking capacity, If you look at a circuit breaker, you may see 6,000 or 10,000 in a rectangle. Go to an old one, the 3871, it might have M9 written on it or something like that. But yeah, these are the levels of capacity of current that the device can tolerate and still remain in service. If we exceed that, it'll probably work, but no longer actually work after a single event. If we have something like a 3036 semi-enclosed rewirable fuse, it may be that it just blows up, which can be a danger. So we need to monitor the prospective fault current, and we need to make sure that the braking capacities of the devices are always within tolerance. And a good example where this can happen on a periodic as a problem is when a property has an increased demand, and so they have an increased supply, and maybe they convert their supply from a TNS to a TNCS system. So that will lower the external loop impedances most likely. And it might be that they've upgraded the switchgear, main switchgear, but maybe subsequent switchgear hasn't been upgraded. They've just refed an existing system. And the existing system may have been fine previously, but it might be now that you've obviously introduced a much better, lower fault loop impedance, short circuit current pathway, but now this distribution gear is vulnerable because of the high levels of energy that will occur. So with periodics, we need to verify if any upgrade in distribution or introduction of larger parallels or anything like that has happened and subsequent switchgear has not been considered for selection. Checking the phase sequences, that's obvious. If we have three phase, it's applicable. Single phase, it's not. If we have three phase, we need to verify that L1, L2 and L3 stay in sequence throughout. There are many systems though, you'll see this on periodics anyway, there are many systems where they're out of sequence, but they're kind of kept that way for the sake of sanity and equipment and machinery. As long as it's monitored and it's documented, that's fine. It must be clear. From an initial verification perspective though, you'll verify the phase sequence energized at the source of supply when you do your ZE and your PFC, but you won't verify it energized throughout the rest of the system, because people in girls etc would say, oh no, you could do the phase rotation verification when you do the R1 plus R2 part of your continuity testing by doing L1 to L you can do R1 to R2 of L1, then you can do R1 to R2 of L2, then R1 to R2 of L3. So you can identify L1 from L2 from L3 at that point. That's what they say. From initial verification perspective, I guess that makes sense. Functional testing, I see a lot of people go, yeah, that's just a tick thing. Once you've done your RCD test, you do your RCD tests, the last thing is you go and you trip it and that's done. That's true, the RCD test does require functionality verification. If you look at the schedule of test results, that is all that it really now asks you to record, but you need to know that the functional test is not just that. You need to verify the functionality of your overcurrent protected devices, your MCBs. You must verify the functionality of any dimmer switches, control switches, thermostats, anything that functions. You need to verify its function. On initial verification, yeah, you can buy stuff brand new that doesn't work, so you need to verify the functionality of everything. On a periodic inspection, you can just assess, if things are suitable for use, and you can just verify it by the fact that people have been using it. You can ask if things don't work. If you have an area where that isn't commonly occupied, you maybe want to functionally test some things yourself. Your isolating switches, for example, they should be functionally verified. This is a big problem we have over in the HV world, where we don't have sufficient functional operation of the switchgear because no one likes to go near it. But yeah, you need to verify the functionality and the reliability of every device. This will include, later on down the line, devices that are supposed to disconnect, like arc flash detecting devices as well. So this will be interesting to see how we're going to do that. And the last one there, the verification of volt drop. Now, from an initial verification perspective, the verification of volt drop is confirmed with the design. The designer has calculated cables, he's calculated sizes of conductors, lengths, and he's accommodated volt drop in his calculations. So all you've got to do to verify volt drop from the initial verification perspective is verify the design has been met. If the design has been altered, cables are longer, cables are smaller, these two problems will create a concern for verification of volt drop, and you should really get that re-verified by the designer. From a periodic inspection point of view, there could be additional runs reduced cables, damaged cables that can incorporate volt drop, changing in loads, changing in the design currents. They can all change volt drop. So what we could do is we could do a measurement of the R1 plus Rn, and then we can calculate that. There's a method that the NIC commonly push, which is R1 plus Rn times 1.2 times IB, I think. There are ways to verify. What we're not supposed to do is go to the source, the voltage is 244, go to the end, the voltage is 236. We're not supposed to do it that way. We're supposed to actually measure a resistive value and calculate the equivalent volt drop. That's what we're supposed to do there. Okay. Alright. Again, I've just flown through that list because there's too much for me to do in this kind of small video on here, but I'm going to introduce some videos that cover each test in a bit more detail further down. Don't worry about that. If you look on YouTube, there are more anyway. 4.7. The learner can identify factors that affect the result of each test. So, how do temperature effects affect the resistance of a cable? How do they affect the current carrying capacity of a conductor? Parallel conductors. If I take a measurement of R1 plus R2 and I expect to calculate the end, if I measure, for example, on a socket outlet circuit, the little R1, the little Rn, and the little R2, and I anticipate that the little R2 should be 1.67 times little R1 because that's what the college say. On an insulated system, maybe in domestic with twin and earths, fine, but in the commercial world where we have steel conduits, trunkings, trays, metal cladded systems, all earth to the back boxes, unless you pull all of those parallels away, which you're not going to, your little R2 will be substantially lower than that. Well, it should be. It shouldn't be higher, that's for sure. So parallels will have an effect. So we need to remember two things with parallels. From the initial verification point of view, we must remove them, or do the testing before we introduce them. From the periodic inspection testing point of view, we have to understand them, not accept them, but more work with them. We need to always read numbers and understand values. And if the question of the value is given to parallel, it's going to be a lowered value than expected. A parallel would not result in a higher value, that's for sure. That's fine, as long as it makes sense. It's got to make some sense. But parallel conductors will result in values not matching what you'd expect them to be. Loading. Yeah, factors that affect the result of the test. Loading. If we have sufficient loading, we're going to have sufficient temperature increase. Okay, so we need to consider the loading of the circuits when we test them. We need to safeguard the actual equipment as well. Preparation for the test. Nulling. If we do not null the test leads for continuity tests, we have lost accuracy. We don't need to null for insulation resistance though. Okay, so make sure you understand why you null. If you understand why you null, then you shouldn't look like an idiot when you're being assessed. Okay, because you know, nulling is important, but only when it's needed. .8. The learner can interpret the result of each test. So, here's an example. I've got a continuity measurement of 0.63 ohms. It doesn't take an idiot to go press a button, see a number, write the number down and move on. You must actually look at a number and say yes, no, or let's try again. You must accept the number. That's what the competent person does. So if you have 0.63, you've got to say to yourself, right, from an initial verification point of view, does this match the designer's predetermined value? Because the designers should give you some predetermined value, or you should have calculated it yourself. From a periodic inspection point of view, then you've got to understand a bit yourself. So what's the cable size, what's its length, does it make sense? If I had a cooker circuit, for example, that was within 20 meters, 0.63 is way too high. If I had a 2.5 cable that was of a sufficient distance, then fine. But I know where I can go to for the data. If you look in the back of the on-site guide or the back of the guidance notes 3, there are tables, resistance of conductors in milliohms per meter. Get an understanding. I mean, the more you do testing, the more you'll understand how resistances go up as you play with cable sizes and length. But develop an understanding on that. If your instrument is saying greater than 299,000 ohms, it's likely that you've got an open circuit between the 2 points of your measurement. With insulation resistance tests, as I said earlier on, we go with we've got this common reporting of greater than 200 because it's always brilliant. What you need to remember is if you test installation resistance test and it's a great circuit, there's no problem, yes, you'll get greater than 200 mega ohms. If you also do an installation resistance test and you completely cock it up, such as leaving the circuit breaker off or having a break in the circuit between the conductors that you're testing, you'll also get 200 mega ohms because there's no resistance when there's nothing in circuit. There's great amounts of resistance when there's nothing in the circuit. I saw a guy actually being assessed once, and he was doing installation resistance tests, and he was getting greater than 200, greater than 200, and greater than 200, and even on the circuits I'd introduced faults for him, greater than 200. And it was only when I asked him to check again and check his instrument, he realised that he had one of his leads in the wrong port on the instrument. They weren't in the positive, in the negative. They were actually in the wrong ports. So do take your time with that. If you have a measurement such as a 0.21 mega ohms, then this is obviously, it's not a short. That's a key thing to say. A lot of people go, oh, you got a short because it's a low number, it's lower than 0. That's still 210,000 ohms. That's a lot of ohms. It's going to be a load of some kind. There's going to be a big load in that circuit. So you're most likely testing between two live conductors, and you've not removed all the loads, most likely. If you have 0, 0, 0, then you've got a short, and you've cocked it up. 4.9. Explain how test results are verified for compliance or classification. So we've just kind of discussed how they're verified, but how they're classified. So we know about the classification: C1, C2, C3, FI, and unsafe situations with regards to condition reports. So with condition reports, we have C1, which is a danger is present, and a C2, which is there's a potential danger present. Potential danger, I translate that to mean a single action will introduce danger. So if I have no earth, then that's not dangerous, so it's not a C1. But in an earth fault condition, which is a single incident, it will become dangerous, which would be a C2. So your C1s and C2s are potential danger or danger present. That would be an unsuitable, unsatisfactory report. C3s is when there's improvement recommended. We used to do codes for all silly non-compliances, but this is only going to be used where you have a good advisory to improve something. So there's been a regulation change, or there's missing labelling, which again would make the system safer, but the absence of some labelling doesn't really warrant a potential danger. So be sensible with those. I'm going to probably cover some coding in a separate video because a lot of people are passing different opinions on coding. The best practice guide that the Electrical Safety First produce, it's not bad, but I disagree with some of that. So yeah, everyone's down to interpretation, and I guess that's healthy. With the initial verification, though, as we said in the Outcome 3 video, with initial verification, it's either yes, it's acceptable, or it's not applicable. You do not report that it's unsafe because it's a signing off exercise, so you wouldn't do that. Okay, that closes the testing chat. Now it's a lot of words, a lot of talking, but as you can see, that's why. A lot of questions, a lot of criteria. Now I'm gonna start working on producing some videos. I'm gonna do them in little videos because of the quantity for these performance outcomes, but these are all performance outcomes on the Outcome 5. So bear with it. It might take a little time, but I'll try to introduce these as quick as I can. Alright, have fun reading guidance notes. Look on YouTube, there are many other videos. I'm going to put some links to a couple below because there's a couple of good ones, and I'll see you very, very soon. Cheers.